Thank you, everyone. So it seems like engine is running, flex capacity is flexing. Let's do it. Okay, well, first again, thank you for coming. So we hope not to disappoint you, and you'll find this time well invested. So we arranged this type of session first time in Arizona of this year. And usually what you see in the sessions is companies present, their products, and everybody saying how great the products are, best in the world, and all of that, right? Which is fine, right? That's what companies have to do. But we came up with a different format where instead of us talking about how great our products are, we let users like you present their experience on the applications that you also can benefit and learn from. And this is the session from this year ICP Winter Conference. So we decided to repeat this format because it's very successful. We recorded the presentation. They were available on our YouTube channel, and we publicized it through our marketing campaigns and LinkedIn and everything. So with this, I'm going to start to do very brief introduction in case you guys don't know who we are. So we are TSP, or Texas Scientific Products, and so we offer a set of ICP or ICP-MS consumables, and we're trying to become or be a one-stop shop for all your needs for ICP. And we started our company in 2004. So we started with 3 partners, and when I put this amount of years, so that looks a bit scary when you talk. It's actually over, when you combine this, over 100. But so we all work for ICP manufacturers. We all get experience in different levels or application and sales and training and service. So this is what we bring to our company and then transfer it to you to serve you. So we approach our customers from the point of view of trying to build the dedicated relationship and coming from the trying to understand deeply your application and then offer products based on your application rather than, okay, well, we have that, why don't you get it? It's great. So that's how we work. And that, I think, will conclude this for now. I will stop, and then I will pass it to our first speaker and introduce him to you. Max?
Yep.
Okay, so laser pointer is working. So Dr. Max Bonner started his lab career at age of 10. So his father, he started company in 1981,
yep.
Right? And then Max was working there, and then after doing his bachelor, he went to University of Florida and did PhD, University of Florida and Brookhaven National Lab.
Yep.
So he did a PhD, then he came back to family business and started to run it, started to work as a trace metal analyst, and then get his ways. Now he's CEO. Under his guidance, lab increased 60% of the sample throughput, right? 61%, I'm sorry. So then he gets some recognition from like programs of contaminants from CDC and all of that. So his lab is well known around the country. With that, I'm passing this to Max.
Thank you, Sergey. So Again, we're going to go over some of the products that we came across several years ago when we're looking at really challenging samples. Nothing here is, quote, groundbreaking, I will tell you, but I think at the end of it, you'll be able to really kind of pinpoint some avenues that you may want to address to get some products that are very beneficial. So again, our lab, if you know, this lovely trailer that looks demolished, that's where Dad started his lab in 1981. It was actually a dressing room trailer for Muhammad Ali. I don't know where he found it, but he founded it. And it's still on premise. If you can look at the Google map right here, that's still the trailer that he refuses to get off the property, so we know kind of where we started and came from. But currently we're at 20,000 square feet in our facility, and we probably need some more room with what we've done on sample throughput. So in general, through the lab that you'll see is we do have dedicated petroleum, microbiology, classical wet chemistry, and then organic and inorganic departments. But you know, for an environmental lab, we're pretty much full service. It's all under one roof, but for us, accreditations are what brings business in. So we are NELAC certified through Louisiana. If you're in that genre of environmental business, be more than happy to help you there or add something to our scope if you need something specific. We do drinking water certifications. The CDC certification that you see is the ELITE program, which is specifically geared to Legionella. It's kind of a hot topic, especially with the hospitals. And we see a lot of that. So just for the CDC, we're the only lab in Mississippi that participates and certified in that program. For me, the one that you see down here at the bottom is EPA's program. That's what I deal with. It's a contract laboratory. We're talking high throughput samples, anywhere between 1,000 to 3,000 samples a month, and you have no idea what's coming to the lab. They give you no information. So there's a lot of maintenance and issues that you have to do to make sure that you're not continuously down and working on your instruments.
Just move the mic a little bit. Keep going, keep going.
All right, so if you kind of look at what we're trying to do through high throughput is really three scenarios. One, really concentrate on your prep work, get good instrumentation in, and then really concentrate on the introduction system. So for us, we get a lot of products from Environmental Express. They have different filter mechanisms that you can use, or you could, we could go old traditional way with a 0.5 filter. Of course, it takes time, so time's money. We're not as productive, so we got to figure out how to do things at a pretty rapid stage. But they're all good products. This filter mate that you see on the bottom left is a product that we use a lot because you're simply just pushing it in and it's pretty much a go process, all right? But for us, we don't use a filtering every single time because we have to know our samples. So if you look in some of these top pictures, we actually have lead chip paints where we're having to actually push filter it, where we may look at something from the petroleum field or this sample that came in yesterday that creates some issue because it's supposed to be an old water separator sample, and obviously their old water separator is not working. So that creates some more issues. So it's always a constant battle between our analysts to know what the samples are. And again, for us, what we do, a picture is worth 1,000 words. So this really gets us out of a lot of trouble, when we're trying to talk to clients because we're directly seeing it. One of the things that we work with EPA specifically is, I don't know if anybody has put an environmental sample, heavy acids in a centrifuge, and the top come off or the tube break. It's not fun to clean up. All right, so we ran tandem samples where we were actually sitting the sample overnight, 24 hours, and comparing it to a centrifuge sample versus just sitting on the shelf. Pretty much exactly the same number. So through our method development, EPA granted us the right to actually be able to take care of samples like that. So we're minimizing the amount of filtration that we're doing. If we go to the next slide of really evolving, we look at this lovely slide up here where we were starting with Cirruses, and for some reason one of the presenters is sitting on top of of the old Sirius's, but we progressed from these really big instruments when I was, really small that they could probably fit me in, versus using pretty much dedicated thermo instruments where we're looking at 6500s that are duo, so axial and radial view. And here recently we've gone to the XP, which really has increased our efficiency because we're really running samples at 2 minutes and 15 seconds a sample. If you're looking at the 6500s, that's 5 minutes a sample. Okay, so it's moving fast enough that you can't quantitate as it's going. You're literally letting it run and then going back and looking at your data so you can do a lot more things at one time. Minus the instrumentation and picking out the right instrumentation, the introduction systems we know are the key. That's where you're going to have the majority of your problems, so you have to know your samples and make sure that it works. Everybody has kits. When you buy an instrument, they all have kits. Now, is that kit right for you? You have to make that decision. And probably those of us that have been doing it, it's not necessarily right. A lot of things you may not use in that little kit versus things that you will. So there's a mixture of what's right and what's wrong. When you come into these particular situations, that's when third-party companies like TSP really help you. Any company, because they have something else that you can look at and try, see if it works, if it's more robust. And that's, as we go through, is what you're going to see. For me, concentric, mirror mist, that's what I grew up on. Mirror mist, awesome, until you touch the tip, and then you throw it in the garbage can. So you really, as you're training and bringing people along, you have to teach them all just the little fine things so that you're not constantly buying all these consumables. But if you're looking down here at the bottom, you have the XL, and then you have the Ion. We have a lot of work on the Exxon, or the XL. The Ion, I have a lot of personal experience with the Ion running ICP and MS, both great nebulizers to consider. So where does this get us? So why did we decide that we needed to start looking elsewhere for different nebulizers? In early 2019, Spartan Mosquito, Hattiesburg-based company, had these solutions, heavy sucrose, like 5 to 10% sucrose, that had sodium or boron in them for mosquito attractants, okay? But they were trying to get it registered through the EPA because boron is a pesticide, so they have to get things registered. So, but if you look over here in the big gallon jug, this is it. You literally have yeast that is suspended in 5% sucrose. It gets on you, it's sticky, it's nasty, and so you're fighting particulates and high TDS. If you look at the bottom right, down here, you can see just by push filtering it through a 6-micron filter that there's a tremendous amount of particulates that can get in that sample line or the nebulizer. So for this, where do we get in the next point was we didn't need to worry about MDLs. We just needed it's heavy concentrated. So I think some of the discussions that I heard yesterday on the floor was a lot of people were running like really heavy concentrations. So we started gearing towards what could we do to help us alleviate some of our problems. In July of 2019, I published this on PlasmaChem. Great source if you're not on PlasmaChem. Great source of information. I was running these samples and it was taxing. Everything was clogging. We couldn't get good results. So we come in and lots of heavy dilutions. And so I proposed all this like, hey, yeah, we're seeing clogs here from the sample lines, sometimes the nebulizers, but when we were placing the sample lines, we were still having to clean and soak the nebulizers, concentric nebulizers, for 24 hours in aqua regia, just to get them to function back to somewhat normal. So you can see that, yeah, very taxing and a lot of consumables. So the thought process through talking to some of the vendors initially was, well, what if you put like an inline filter in and tried to do an auto dilution system? Okay, well, auto dilution systems have evolved. There's some good newer products out there that we're actually looking at, but we had sucrose, and I wasn't really reluctant on putting heavy sucrose in an auto diluter. And then 2 inline filters to monitor it, great, but we still have to do maintenance on it. So we weren't fixing the problem. That problem then persisted, and I will say this was probably posted on Plasma Chem for maybe an hour. And then Sergey, being Sergey, literally picked up the phone and called me. He thought it was my brother because they went back a long ways of working. But Sergey was like, hey, let's talk about this. What are you trying to do? So again, when you go to the application guys, the more information you give them, the better success you have, right? So our whole deal was with boron specifically, we were calibrating from 2 ppm to 5 ppm. From my knowledge, with the introduction systems that we had, with the torches, all that good stuff, we should be able to wash out and get our baseline back down for the next sample. That wasn't happening. So with the conversations through Sergey, it's like, all right, your method is correct. We just need to help you on your nebulizer. And if you really think about a concentric nebulizer up there, very, very, very small sample line, right? 0.15 to 2.5 millimeters, so you're looking at like less than 70 micron particles. I'm talking, you could see the particles, the yeast in there. So he told me, of course, he kind of, I would say, had the South Mississippi talk to me, and he said, look, we can put gravel through our nebulizer. Gravel, that's very interesting. Okay, I said, send it. And I, we kind of maybe made a deal that maybe we would try it out, see if it worked, and if it worked, we would pay for it. I'm telling you, within a week, I sent a check to him because it worked. It worked very, very well because you can see just the sample line of how big that hole is that your sample's coming through. So anything that's sticking, anything high particulate, high TDS really, really helped. This slide may be a little hard to see, but for us, when we started using the Excel, we were able to really identify 2 key trends. The one trend was that when we held our standards at plus or minus 5% or 10%, we would start looking at some deviation. So we could see here where when we started dropping down on percent recovery, then we were looking at, hey, we needed to wash out our system. We needed to clean our system. Or when it got really close to 2 sigma, it was time to clean it and make new standards. So there was a really true trend to it. The more important thing is this. We had in the very beginning, using a concentric nebulizer, 59 to 32%. Okay, that's reanalysis. When we went to Excel, we cut that down to 19 and 13% reanalysis. That's huge. Nothing was sticking, nothing was clogging. We were going through 4 to 7 nebulizers a month off of concentric. We went to none, absolutely 0, and you could actually see some of the particles pass through the nebulizer, and they just hit the spray chamber and are taken out. Then we go into the next step of, hey, can we take this for our routine analysis? So 2007, my brother and Paul Gaines from Inorganic Ventures started working on making a calibration with basically like everything on the periodic table, all right? And so we could fit that into all of our runs, how we did things. Everything in red is what we calibrate on a daily basis, and everything's passing QC for 200.7. All right, so you're looking at plus or minus 5% on an ICV. All right, so it's very customized, and it allows us to do a lot of things. We wanted to make sure that Excel was only for boron for this sucrose thing, but how could we do it if we didn't have to change nebulizers out? MDLs are MDLs. We can argue back and forth about them, but when you review the results, what you really see is no real difference between the Excel and the concentric. All right. When I saw this, it went straight back to Sergey's like, hey man, can you really look over this? Because we really need to know if what we're seeing is right. And everything that we reviewed, it's just pointed to, hey, we can still do our analysis with one really, really robust nebulizer. This was another case, and I'm going to bring it to the next slide, which is pretty interesting in the fact that I personally did this. This was a 2,000 sample load that required 80% reanalysis because manganese was running like 100 and 150 ppm in solution. So we ran it on the XP, and it was super fast. It was wonderful. Sitting there and turned this into the EPA. If any of y'all have any information or looking at like 3050C, I highly recommend you look at that method. 3050C fixes the problem with antimony. This was a big problem because EPA was having to reject all their data. But from all the boron analysis to these 2,000 samples, this is the really important key. So July 2019 to July 2024, off of one nebulizer that we had to retire, we ran over 250,000 samples, QC, and calibration curves. We never cleaned it. We never back flushed it. We put it in the spray chamber. We tuned it. We looked at the yttrium bullet, and we let it run. That's pretty impressive, okay? So it's highly robust. You can't really clog the thing, and it can do really high tow solids. The thing was with Sergey was like, what do you not like about it? And I said, when you drop it on concrete, it breaks. Okay, so Sergey had this other idea. He goes, well, I got a new nebulizer for you. It's not new, but I think it'll work for you. It's made out of plastic. Great, I can drop it and hopefully it's still good. So we went into, and this has been, what, a week that we've had this, so we've really pumped this up to see if we can use this nebulizer. The information here is you always have to have a comparison, right? So for the new software, any new software allows you to do neb optimization. This particular one, so we don't get to do it manually anymore, we're doing it by the software. So this actually goes through and optimizes and looks at the intensity of manganese every 0.05 liters per minute. Okay, so you're seeing the profiles, you're getting the profiles, and you're assigning the neb gas. All right, so the computer's really doing that. So this is our base. We're looking at 0.5 to 0.65 on axial or radial. When we looked at this nebulizer, it was really cool straight off the bat because it almost tunes exactly the same to something that you have in your lab. You've got concentric nebulizers in your lab and it tunes almost exactly the same. In some areas, we're seeing more sensitivity than on a concentric. That's impressive. Low wavelength, that's impressive. All right. The cool thing about this, I'm not a guy that likes to run switch neb gases because you can do it. Run one axial at 0.5, 6.5. I'm not that guy. I don't like it. I don't like things moving. All right. But if you really look at this profile versus the concentric profile, you can really almost mirror those up, change the gas flow manually just to a little bit to where you're really running at 0.55 and you're almost getting max sensitivity in axial and radial view. You're not going to see it in a concentric. It's really hard to see it in other nebulizers. It's very, as far as analyst goes, this is what you want sitting on the bench, training your folks. There's not a lot of room for error. Okay. So with that little take-home message, acknowledgements, we like the whole thing of install it and forget about it. I will ask all of y'all to please keep training people. You know, the guys that are the apps guys and the engineers, at one point in time, they're going to retire. So we need the next generation of guys that will really retain, and ladies that will retain information. I get to deal with a lot of college students coming out. Not always impressed with what's coming out of the universities. So please, like when you're sitting there, like literally teach these people, get them to problem solve and get them to retain their information. As far as nebulizers go, yeah, they do the optimization. We have something that's robust now compared to anything else. And if you're getting 250,000 reps, that's just documented, by the way. That's not all the stuff that didn't work. You have something that's really robust. So acknowledgements-wise, all the guys at Bonner and ladies, they're the ones that make everything work. I just sit back and kick up my feet, you know, and watch data come through. But again, TSP, great service, not only just talking with, you know, Sergey or giving those conversations, but the people that they have kind of on the outside that you may never see as far as getting your quotes ready, making changes to them on the fly. I mean, you're really not going to find too much better service than TSP. So with that, I'd like to say thank you. I probably ran over, but any questions, I'll be more than happy to ask.
Questions, please?
one that's not necessarily pertaining to the nebulizers. I'm sorry, but I saw you were using those filter mates.
Yes.
Did you have trouble with those with oil coming through them and not filtering that out?
Yeah.
Max, would you mind to repeat the question?
So the question was for sample prep. I showed the Environmental Express filter mates. And do you have problems with filtering oils, right? Yes,
Okay.
we do. Again, when you're going through these filtering steps, it's all what resources do you have, and you know they may not work. Sometimes you can just look at the sample and know, hey, this is going to work. So probably what you're seeing is what we see too. Yeah. One more, real quick. Mike.
So the slide about, great presentation by the way, the slide about the optimization was very interesting, but the question I have is V-group nebulizers. Two questions. Have you tried V-group nebulizers, since those are can be used for high matrix samples? And if so, what was your experience with them, and how do they compare with the nebulizer that you're using here?
Yeah, so we haven't used V-Groove. We were solely, that's 2019. That was quite a few years ago. So we were truly just concentric and mirror mist, and then we flipped over to the XL. So yeah, I haven't personally used any of the V-Groove.
Okay, thank you. Sorry, we're a bit of a pressed for time now, so just 1 second. Okay, so when Max shared with me last week that, so he got this nebulizer since 2019, so I tracked it down. And then he sent it back to me because, something was, it was a restriction on the gas channel, something built up there over the years. So then he said, well, we ran over 220,000, 250,000 samples. So we decided, so that's quite an achievement. And we're going to start 200,000 samples club, and Mike is awarded with this nice achievement of getting that. That's not it. That's not it.
Appreciate it.
So
thank you.
he told you that, yeah, the nebulizer quit in 2024, which is, hang on 1 second, which is, yeah, true. So he sent it back to me, so I tried to backflush it, nothing worked. And then last week, so, well, let me try it again. So I did a little bit of a more of an extensive cleaning, and just, basically I soaked it in the detergent and just heat it up. And there we go. The back pressure is back to normal. You can get rid of this. So
I'm not going to.
I wish you 250,000 samples more, man.
Thank you. I appreciate it.
All right. So let me introduce you to our next speaker. And bring his presentation up here.
Oh, thank you.
That's Mr. Dion Saridis. He's VP of Analytical Services at Pure Lithium Chemistry.
Lithium.
Right? Yeah, Pure Lithium Corporation. So he's the expert for ICP instrumentation. He's been working for major manufacturers. So any kind of sample that probably exists came through his hands. And I had the privilege to work with Dion for a while. That's why I have so much gray hair. So Dion serves on, well, he's familiar with ICP in all the aspects, you will see it in his presentation. He also serves on the number of committees, including the ASTM committee, AOAC, and so his presentation with the chemical company is Pure Lithium, which is the sound topic now, and he deals with many, many matrices that even if you're not in this industry, but we felt that you will benefit from hearing about his experience with different matrices. And the so he authored numerous publications, and he currently exists in the development and commercialization of first high amperage lithium metal battery for pure lithium.
Thank you.
All?
That's it. Go away.
One
now.
thing I missed,
These people have to leave at some point.
he also was part of the commercialization of first ICP to do halogens.
Yes, thank you. All right. So the first half of my presentation is to let you know what we're doing because it leads into the second half. The battery technology we're developing, by the way, before I offend anyone, is ExxonMobil here? Anyone from ExxonMobil? Raise your hands. Oh, great, I can tell the story. So we're working with Stan Whittingham and Don Sadoway. Don's our co-founder with Emily Bowden, who was at Argonne National Labs. Lithium metal batteries is the next generation. You'll see why these batteries are so revolutionary. It's literally like comparing a DVD to a solid-state drive. That's how different this is. But to get there, there's a lot of material testing that needs to be done. I am on the ISO TC 333 committee for developing methods for this industry. It's a very cowboy mentality. You know, the tests people are doing, no offense, Chris, they send lithium out to environmental labs and they wonder why the numbers, don't match what they should be in terms of molarity. And that's one of the things I'm going to discuss. So I'm going to talk about brines in the second half. Everything we do, whether it's the electrolytes, it's the anodes, it's the cathodes, it's the raw materials, works or comes through an ICP. We tried MSs, we've tried graphite furnace AAs, we've tried XPSs, which is more topography, so there's a reason ICP is the industry standard. Almost every single ISO method we're developing is centered around an ICP, some of them an IC, but mainly ICP. So the second half will be specifically about the analytics and how we've been able to optimize our matrix tolerance. So, quick background. Lithium metal batteries, these are the holy grail. Why? We control the supply chain. If you ever see how a battery is made today, it's insane. Oh, the lithium comes out of Chile, and then it goes over to be processed, and then you get graphite shipping over from Asia, and then the U.S. prepares the anodes and and then it goes back over to Japan to make the batteries, or Korea, at Samsung, or China. It's insane. The cost is astronomical. So this technology came about when Don Sadoway came up with the idea that says the cheapest way to make something is to make it from dirt. And that's literally what we came up with. We said, if there was a way to extract lithium from a readily available source without mining it, it's going to, revolutionize our ability to make batteries. And the lithium metal battery design fills that void. The other thing it does is it monetizes basically a byproduct of the petrochemical industry. So instead of just taking these oil field brines and pumping them back down, you can actually drop a battery plant right there next to it. And that's where we are in this. Our next phase now is actually building a battery plant up in Canada at an oil field. Okay, so you can imagine we have a lot of investors from the petrochemical industry that we're working with. So ultimately, our goal was to get below $50 a kilowatt, which is considerably cheaper than lithium ion. Secondly, the battery is I don't say fireproof completely, but it's fire resistant. Like, you can dunk our battery in water with the exposed surface and nothing happens because of the separator we're using, all right? And it's much lighter and packs more energy. So it's going to be suitable for higher density applications like automobiles down the road. But how does it work? You literally have your oil field brine. We create a electrode, and then the battery is printed. We literally print the battery. So we have the foil coming in. This is not a physical deposition. This is an electrochemical deposition. So traditional plants on the left, you can see how big it is. It takes 3 weeks for battery completion with regards to the formation cycles. You're taking, lithium. You're doing a DLE. DLE stands for direct lithium extraction, and then you're converting it to some form, a hydroxide or a chloride or a salt, and then you're putting it onto the cell. And with our technology, those cycles take 1 day. You know, in what used to take literally weeks can be done in a day. It is a tremendously efficient process. So if we looked at it step by step, the bottom represents how this works in a traditional lithium-ion application. The top is how we're doing it. So dirty oil field brine, we extract the lithium out of it. There is a DLE process in between to concentrate, because obviously the more concentrated the lithium is, the longer the process can run without any maintenance. So even if the lithium is coming out at, you know, typically let's say 50, 60 ppm in the brine, to concentrate it to 700 is nothing, and then, to do a DLE to pull it out at about 700 and then concentrate it to anywhere from 2,000 to 5,000 is very, very simple. And that's what the company, on the previous slide you saw, E3, is what they're doing for us. We just entered a cooperation with them. Our pilot plant's going to be up in Canada, where E3 is located. All right, so why is it better in terms of that? We've eliminated the graphite. Graphite adds a ton of weight and mass to a battery. So you can see physically from this diagram your traditional lithium ion versus lithium metal. You can see the separator, and you can see here our negative electrode, how thin it is. And it is just a compact, high-energy battery. Cost-wise, if we look at where you can get lithium from, ingot extrusion, not cheap. Physical vapor deposition, also not cheap. Currently, our target was $50. We're at about $16. We want to get down to about $6.70. So this is a big, big deal to be able to take, like I said, a byproduct like an oil field brine. Lithium-ion batteries were developed in the 70s by Stan Whittingham. He just won the Nobel Prize about 3 years ago. Stan Whittingham is actually working with us, and Don Sadoway. He developed it in the 70s for ExxonMobil. ExxonMobil was like, this is great. Okay, thanks. And they threw it in a drawer. It literally just sat in a drawer, the lithium-ion battery, until a company called Sony came along and said, we got this thing called a camcorder, and we need an energy source for it. The patents had expired, and Sony is really who brought the lithium-ion battery, you know, into the mainstream fold. This is the next step. So analytically, you know, what do I look at in the lab? I'm looking at minimal every day, at least 1% to 2% total dissolved solids, but these oil field brines can go much higher. We've run up to 30% saturated brines, and you can imagine they've got sulfur in them, they've got oil in them, but most importantly, they have lithium. Okay? We run high purity lithium. After the process, our lithium is typically over 99.95% pure. We have reagents that are coming in through the door. They can be anywhere from DI water to, you know, high purity acids. So we do a lot of sulfuric work. If you work with lithium, you know you have a lot of sulfuric acid. It's a very dirty acid, so you know you need to monitor its purity. Organic electrolytes, you know, ethylene carbonate, you know, ethyl methyl carbonate. It is so many, DMC, IPA, isopropyl alcohol. And alloys, you know, copper alloys, aluminum foils, iron foils. And finally, we have polymers, which is what we use as a separator, and even slurries, because we'll test electrolytes that are in slurry form. So if I missed something, please let me know. As I mentioned, we're on this committee, so we're developing this methodology. ICP OES just offers us so much more flexibility. It's just so much easier to use. With a mass spec, you introduce a ton of mechanical error. You're diluting the sample considerably more. When you multiply everything back up, you get unbelievable standard deviations that you just can't repeat, because every chemist is different. So if lab tech A is working one day and they're very good, you might get tighter spread on your results. If lab tech B is, you know, a little sloppier, they'll be all over the place because of the dilution factors. Also, on our particular system, and I know a lot of you might not be able to do this, we have to work with a rolling circle. We need chlorine, bromine, and iodine at very low levels, and the shells can't do it. There's too many optical components. Also, we need resolution. Group 1 and Group 2 elements are critical for us, so we need high resolution in terms of those elements for a specific reason you'll see later on. Sample prep and turnaround has got to be simplified because, like, if I'm not in the lab, I have to have a technician that's running it. They're not spectroscopists. I'm working with engineers. You're looking at the only analytical chemist in my entire company. But I have to be able to make sure the facility doesn't shut down. And finally, the maintenance requirement. If it's simple to use and anyone can use it, you're just going to be more efficient. So, how do we get there? This is an oil field brine. You can see it's beautiful, completely engulfs the plasma. Okay, we do use a laminar flow on this, so it does not salt up the torch. We can run 8 hours continuously with nothing more than cleaning the interface. This is a radial view. We run almost everything axially because we don't know what's coming through the door, and that includes sodium, potassium, lithium, because we need, in some cases, ppb to sub-ppb detection limit. We do measure a lot of the Group 1 and Group 2 elements below ppb, than parts per trillion range. So what's the difference? Well, radial plasmas are going to give you high stability. They got matrix tolerance. You get better linearity. You less matrix effects, but you're going to trade off sensitivity. You're not going to see sodium and potassium and lithium at parts per trillion or single-digit ppb on a radial. It's just not going to happen. But in an axial, you will. So that's the trade-off. On the axial, you're going to get much higher sensitivity, but unfortunately, you have EIE effects to deal with. They're less suitable for total dissolved solids. Organic compounds typically don't work as well, or you need oxygen. You will have to bleed oxygen in there. And linearity and accuracy are concerned. You can address these. Like I said, with oxygen. You can use an ionization buffer, again, but you're adding more work. For us, everything's been automated. It might not be practical. It might be easier if you're looking at an application like this to just go with radial view. But for us, we've created a system that's about as bulletproof as you can get. What's an EIE effect? If you don't know, this is an EIE effect. This is 200 ppb. Let me get the laser pointer. What? That's not the pointer. Here it is. Okay. These are both 200 ppb potassium. The difference is the green is in water, and the red has just had 50 ppm of sodium added to it. That's the EIE effect. You're going to see 40–50% error. This is a 200 ppb certified reference material, and the only difference between it is we've added sodium. It cools down the plasma. The plasma behaves differently. The Group 1 elements particularly respond not even in a quadratic form, but almost in a cubic form. If we look at them side by side, you can see the sensitivity difference. It's much less pronounced, the effect here. It's still there on the radial, but you're going to need a lot more sodium and a lot more potassium to see that effect. So that's why for environmental work, people love using radial view for Group 1 and Group 2 elements. For research, and you need the sensitivity, you might have to live with axial like I do. And like I said, there are very, very simple ways to address it. But this is what the calibration curves look like, okay? Axially, without any issues, without the EIE issues addressed, and radially on the right. When we add cesium to this matrix, because we have plenty of sensitivity, both curves look like they do on the right, whether they're axial or radial, and you can extend the curve as far as the linearity of the line goes. Okay, so you can address the EIE effects in brine matrices, but again, it's exasperated if you're not matrix matched. Standard addition is probably the best way to do this, but a lot of labs don't want to do standard addition. Why? It's time consuming. You have to take a sample that's similar or identical to all the samples you're about to run. You have to split that sample into 3 or 4 solutions. You have to spike it, 1, 2, 3. Then you have to measure it. Then it back calculates it. Then you can run all your samples. It's a lot of work. It's a lot easier for me to take pre-made, standards from Inorganic Venture, drop them on there, and let the system automatically add the ionization buffer, and I'm just off and running. I trade off a little sensitivity, but again, I'm working in parts per trillion to parts per billion, so I don't care if I can see 80 parts per trillion aluminum or 160. I just need to make sure, I have the sensitivity I need to do with regards to my sample matrix. Dilution factor is a big consideration. The less you dilute, the less mechanical error you're going to deal with. You're going to get better numbers across the board. Accuracy bias, like I said, can be up to 100% depending on your sample prep, how you set up your plasma, the calibration strategy, and I'll talk about that coming up. ICP OES, again, this is the preferred. I have nothing in ISO right now is outside the ICP OES realm for this type of material, with the exception of IC for the halogens, because as I said, not all ICPs can run the halogens at the low levels that it needs to be, so there is an IC method for those elements. Radial view is better suited for brines. However, they both will work for you, especially if you're matrix matched. I see no practical benefit for dual view in this application. If you're going to do this application and you can meet your detection limits, just go radial or go axial. If you're doing dual view, that's great. You're just slowing down your analysis time. And internal standards, you should always use an internal standard. If you're matching your atomic lines to your atomic lines, your ionic lines to ionic lines, you're going to get better elemental group performance, all right? But the bottom line is if you don't follow these, especially in a brine, now I'm talking particularly in a brine here, if your matrix isn't matched, you can see deviations from 50 to 200%, and that's something we are addressing in the committee. All right. So, how do you optimize, select an ICP OES for, and this is for the lithium industry, it might not apply to you all. Well, in terms of the nebulizer, torch configuration, and spray chamber, you need, as Max, and I know his brother too, Max had mentioned earlier, you need stability, accuracy, and precision. It all starts with the nebulizer. If your sample delivery is not consistent, your plasma conditions are going to be inconsistent. Again, I'm assuming the peripostolic pump's not bad. Your short-term precision is going to be affected. Your long-term precision is going to be affected. If you need good short-term precision and you want good long-term precision, short-term precision is your RSDs. Long-term precision is, does my 1 ppm still read 1 ppm after 50 samples? That's your long-term precision. Does my sample that I ran a week ago still read the same 3 weeks later? Again, long-term precision. And the construction material of the nebulizer is very, very important. Silicon, boron were mentioned earlier. If you don't have, an inert material and your calibration standards have trace HF in them and you're trying to do very low level PPB, boron and silicon, you're going to struggle because the HF is going to affect the glass or quartz surface. So what do we use? We use a Roland circle. That's an Arcos 2. So it's a full 3/4 meter spectrograph. It goes down, a spectrometer. It goes down to 130 nanometers. So we're doing chlorine at 135, 134, 136, and they're all at sub-ppm levels. So whether it's oil or aqueous, we can get the chlorine at low levels. It has a solid state generator, which is very important because when I'm running electrolytes, not all electrolytes are water soluble. I have to use an organic solvent. So I might use acetone, I might use IPA, I might use naphtha, it really depends. The key here is I can run isopropyl alcohol, I can run gasoline neat into our system without the plasma going off. The only thing I bleed in is the oxygen to keep the carbon buildup, because again, I'm running axially. If I was running radially, I probably wouldn't even need I take that back, I would need the oxygen because I need to get low potassium numbers. And potassium and sodium have carbon band interferences. So you want to bleed a little bit of oxygen in there, like less than 0.05 liters per minute, just to burn off that carbon so you get really good performance for sodium and potassium. If you don't, your sodium and potassium numbers, you'll still see it, but your detection limits will go to pot. And then I also run slurries, and this is where the nebulizer, the ultimate, is just bulletproof for us. High dissolved solids, organics, alloys, HFs, slurries, everything through one nebulizer. They rinse it in between and they go off to the next sample. The only maintenance we do is when we're switching from, let's say, a high salt sample or a high chlorine matrix to something that's low. The interface comes out, we wipe it down, we put it back in, you're off and running. So you're literally talking about 5 minutes between nasty matrices with this setup. Precision-wise, the top are calibration aqueous solutions. The BDO1, 50, and 10 are brines. And you can see you're typically under 1%. In fact, these are actually really good. These are typically about 0.5% RSD across the board. Here, we are looking at some different elements in the UV region. Here we're looking particularly at the phosphorus. And again, it's quite good. This is a low-level phosphorus. I think it's 0.5 ppm in the brine, and we're at under 1% RSD. Oh, next one. This one is very important to us because our lithium numbers can run from trace. So I use the 670 line, but that line I can't go over 10 ppm on. That line is parts per trillion to 10 ppm and it saturates. But we're simultaneously measuring 460, 323, and 274. Again, RSD is under 1%. In a brine matrix or a lithium metal matrix at this point, and we can go from sub ppb to percent levels. This is very interesting for us too because we get raw materials from all over the world, and I don't know if anyone else, if you're using a shell, I don't think you can separate this because the resolution is much lower. We can separate lithium-6 and lithium-7 on an ICP OES. That's very, very important for us because we need to validate. When we tell people we can take a brine and we can make a battery out of it, the first thing they're going to tell us is, well, how do I know the lithium is coming out of the brine? How do I know it's not coming out of your, organic electrolyte? You might, because you have to have lithium in both of them. You have to start with lithium in the electrolyte, and you have to start with lithium in the brine, and it's an exchange process. So as you deplete one, equilibrium, it pulls the other one through. How can you prove this? This was when we first started the company, we had to show this was viable. Very simple. We made a brine using lithium-6, and then we ran the process, and then we measured it, and 98% of the lithium we deposited was in the form of lithium-6. And then people were nice enough to give us money. So it's a very good strategy. But again, that's something you cannot do typically with ICP. But we did a lot of homework making sure that we had the right instrumentation for doing this. And finally, I'm almost done. This is an organic material. This is a electrolyte. It's ethylene carbonate, ethyl methyl carbonate. It's a mixture. These are diluted 1 to 10 in IPA, straight isopropyl alcohol. But what's unique here is I'm calibrating with water. I take 1 ml of water, 9 mL of IPA, make my calibration standard. I take 1, in this case, gram, because I shouldn't say mils, because you got to do this by weight. You don't have to, but your numbers are not going to be as good. 1 gram of the electrolyte, and I add 9 grams of the IPA. I shake, I load them up, I run it. You can't buy certified reference materials for this, but what you can buy is salts that are in the electrolyte that have been done gravimetrically. So that's what we did. We bought a 1 molar lithium nitrate in the ECEMC. We ran it against a water calibration curve, okay? Just DI water and lithium. And we did the density correction because obviously the IPA cancels out. You don't have to worry about the density difference because the matrix is 90% isopropyl alcohol. I have to worry about the calibration standard, which is water, and the ECEMC. We applied the density correction. The expected value was 6940, which, as you all know, is 1 molar lithium. You know, we recovered down here in the red, if you can see it, 6924. And we've been doing this for well over half a year. We have tons of data to show this is absolutely a viable way to calibrate this particular matrix. I can't talk about oils because I haven't done oils, but you know, the next talk will be about that. But in terms of organic solvents, especially ones like IPA, acetone, this works for us. And finally, in closing, chlorine. Why is chlorine important? We do not want chlorine in our processes. It hinders the battery performance. This is a scan of chlorine at 136 nanometers. Let me give you an example of why this is important. We buy a lithium fluoride, sulfonated fluoride material. It's called LIT FSI. It's a tetrafluoro sulfate. When we purchase it from 3 vendors, China, Japan, and France. They all spec the material to be less than 10 ppm chloride. Okay, I'm going to say that again, chloride. And it is. It's less than 10 ppm chloride. But in terms of total chlorine, they don't measure it. We're running the material, we have poor performance, we're talking to all of them, nope, less than 10 ppm, we ran it, less than 10 ppm, less than 10 ppm. Again, they're measuring chloride, they're not measuring total chlorine. What we found out, that when they dry the LITFSI, they use an organic solvent, which is halogenated with chlorine, and the residual chlorine is on there. And they have no way of testing it because when they're running their ICs, it's set up for chloride. This is why you know, having an instrument that's capable of this is so important to us. And by the way, the 3 vendors, depending on where they come from, 800 ppm, 1500 ppm, and almost 10,000, almost 1%. So again, we have a quality issue, so you know if we have to buy the material we're going to buy it from. So quickly, electrolytes, salts, alloys, polymers, lithium, with regards to the validation test. These are all things we can do on one instrument, set up with one nebulizing system so that any of the techs in the lab, as long as they put the right solutions on the auto sampler, you know, the right calibration standards, they're able to do it. So, that's it.
Thanks. We have time for probably 1, maybe 2 quick questions.
See, no questions.
Oh, there is? Yeah.
You mentioned the use of cesium to make it quick. Do you use that as an internal standard or just?
Both. I can use it both ways. So on our system, we just tee it in. It just goes in. And if I want to see a little bit better, you know, performance, it's really just for sodium and potassium and lithium. I will use cesium. I'll just say use it as an internal standard. But if not, it as long as, you know, it's within, you know, the sample doesn't have more group 1 element in it than the buffer. So if I'm at, let's say 0.5% on the buffer and I'm at 2%, I'm going to have a problem. But if I'm at 0.5% on the buffer and I'm only at 0.1% on the lithium, it'll work. So I will use it as an internal standard if it's, you know, if it's not there. All right? All right.
Thank you. Thank you. Okay, with this here, I'm very excited to introduce you to our next speaker.
Thank you.
Madeline Ghazi. She's the R&D chemist from Inorganic Ventures, which is well-known producer and supplier of reference material standards for ICP, and we are the proud distributor, premier distributor in the United States. Medline started back in '94 with Dr. Paul Gaines, who is the founder of Inorganic Ventures. And I think we met somewhere around '96, where the probably
99.
Well, yeah,
Well, okay.
around there, yeah,
Okay.
around there. So when Paul purchased the ICP-MS for his business from the company I used to work with, and I was the one who actually ended up installing it and keeping it up and everything. So I was there almost all the time back in New Jersey. So Madeline is one of the few people that I met in my life who really enjoys doing what she's doing, and she even put it, she has a joy of doing it. And I'm at this one, I pass it to her. She's going to be showing you, and I'm not afraid to use this word, a revolutionary research that was done at Organic Ventures by Madeline and under the guidance of Paul Gaines. So the history behind that was back, 20 years ago when we started to work. And I said, well, why did you guys develop the standards for running organics? And Paul said, nah, Sergey, well, I'm not interested to get something like other companies do. I want to do something different. And then he tried to pull up something from the shelf, like chemist, and mix it up. Like the idea was to mix the something that will be mixable with oil and with water. So that was back, I don't know, 20 years ago. But now Madeline took it over, and I'm passing it to her, so she will tell you all the magic behind that.
Thank you, Sergey. It's a pleasure to be here. Thank you for being here. As Sergey said, I'm going to talk a bit about the research that we've been doing in the last year on the feasibility of using aqueous standards connected with organic solvent in the testing of metals in oils. So Inorganic Ventures, just very briefly, we've been around for about 30 years. Dr. Paul Gaines is the founder. Our bread and butter is aqueous standards. We make high purity standards, both single and multi-element blends, custom standards, pH, titrants, conductivity, and reagents. We are able to offer a 5-year stability on our products. Most of our products have a 5-year stability, and that's largely due to a very robust stability program. The origins of the work that I'm going to talk about today came from an interaction with a customer and my boss, Mike Booth, who's the technical director at Inorganic Ventures. The customer said to him, look into organometallic standards for oils. We'd like to see what you can do for us in that area. I'm not going to repeat what Sergey said, but what Paul wanted to do was not use the traditional approach of the organometallic starting materials. His worry about the organometallic starting materials is that there can be an instability with these materials, and everything in our aqueous-based solutions is extremely stable. The metals like a little bit of acid, and so they stay in there. They don't give you any trouble. So we did not know of an approach that used traditional organometallic starting materials. So as I said, we were looking for a way to use our aqueous standards and find an organic solvent that would work with them. So what we found was, yes, we can mix our aqueous standards with an organic solvent. When I first got involved in this work, I saw that the organic solvents that would work with the aqueous standards were going to be extremely toxic. So I did some digging, and I found a possibility. I found a source for organic solvent that is both green clean, and sustainable. And this really got me excited, you know, for the people who are working with this material. Every day in and day out, oil testing labs, they're running hundreds of samples. They're under a tremendous amount of pressure to get these hundreds of samples done. And I'll talk about what we have been trying to do on that end to help them. So we did find this solvent. The solvent that we found allows for the miscibility of our aqueous metals and also for easy dissolution of the oil samples directly into the solvent. So what we have, we built a 6-point calibration curve, micrograms per gram, all by weight, 0, 1, 5, 10, 20, and 50 micrograms per gram of the 26 elements that are commonly tested for metals in oils. These include the general wear metals in oil elements and also the additive elements, and we were able to add sulfur to the mix because we're using sulfur in a form that is miscible in water rather than the organometallic sulfur starting material. I'll show you a little bit about that in a bit. I mentioned it. The oil samples are directly dissolvable. They're directly miscible in the organic solvent. And our customer said to us, it would be great if you could put your internal standards into this organic solvent, because we want to be able to do this easily. What they do is they have their organic solvent with their internal standards. They use it for dilution. Luckily, and I say luckily, this worked. We were able to put cobalt and yttrium into the organic solvent. This is cobalt and yttrium both in the inorganic forms, directly miscible and stable. So this serves as the diluent for the standards and for the samples. And this solvent with the cobalt and yttrium is also usable as the rinse, and that's commonly used in oil testing laboratories. So I got ahead of myself a little bit, and I really covered what was in this slide, except for saying, again, to follow what is commonly done in oil testing laboratories. They normally are doing 1 to 10 dilutions of their samples. We also made 1 to 10 dilutions of the oil samples, and in order to test our calibration standards, we did 1 to 10 dilutions of various currently used organometallic standards available from different manufacturers, and I'll show you the data from that work. But just to go back a little bit, the organic solvent diluent contains the cobalt and yttrium at concentrations that when you dilute your sample, you're going to get 15 ppm, 15 micrograms per gram of cobalt and 5 micrograms per gram of yttrium in there. Again, that's a common concentration of cobalt and yttrium that's used in the metals in oil testing business. Oh, and one other thing. We're a certified reference material manufacturer. As Dion mentioned, we do everything by weight because it's definitely more accurate. Oil testing laboratories, they have the pressure of, again, hundreds of samples every day. So they're using auto diluters. They're doing their dilutions volume to volume of their samples. Their standards are micrograms per gram. They're weight-to-weight standards. But what we have is, we know that the oil and the density of our oils samples and the density of the diluent, organic solvent, they're very similar. So whether you do a weight-to-weight dilution or a weight-to-volume dilution, you're going to be okay on your results. Our ICP-OS system that we use, the introductory system, again, very, very important. We're using a Spectro Arcos 3 ICP-OES in radial mode. Dion was jealous that we have the 3. It's a great instrument. Sorry. I love it. We use Solvaflex peristaltic pump tubing because we're using organic solvents and the oils. We use a twister cyclonic spray chamber. It has a baffle in it and a quartz torch for SOP mode. We also have a dripless sample probe, which is very helpful. We tested 2 different nebulizers, Sergey's Optimist Ultimate Nebulizer and also a more traditional glass concentric nebulizer. That glass concentric nebulizer was made specifically for high dissolved solids. The results I'm going to present are from Sergey's nebulizer, the Optimist Ultimate, and Dion again showed this. The RSDs that we got from this nebulizer really surprised all of us. Considering we were running oil samples, oil standards, organometallic standards, our solvent for any of the standards or samples that were at 5 ppm or higher, we saw RSDs. We are seeing RSDs that are less than 0.2% up to single-digit RSDs. When we got down to looking at samples, oil samples that we ran that are in the less than 5, more like less than 5 ppm, I'll just say, between 5 and 0, we're seeing higher RSDs down there. In this slide, I'm showing you the coolant and auxiliary flow rates that we used for our testing. And the auxiliary and the coolant flow rates are values are liters per minute in the argon flow that are commonly used in oil testing. So we use 14 liters per minute coolant and 2 liters per minute on the auxiliary flow. The nebulizer flow rate for the Optimist Ultimate was optimized at 0.9 liters per minute. Our our plasma power was 1,400 watts. Again, we're at we're in radial mode here. So here on this slide, I'm showing you results using Sergey's Optimist Ultimate Nebulizer under the conditions that I showed you just before. These are the results of one of the 26 element traditional organometallic CRMs that we ran. This particular CRM was at 100 ppm. We made a 1:10 dilution of this and ran it versus our calibration standards. Everything in it's harder to see on there, but everything in the darker green, most of those elements gave results that were less than 3% from within the 3% range of the certified values for those elements in the standard. There were only a few elements that were within the 5% range of this CRM. And I'll be happy to take questions as we have time. The next slide shows results of running an additive element, CRM. Those elements are, let me see, calcium, magnesium, barium, zinc, and phosphorus, all at 1,000 ppm. And then a separate CRM of organometallic sulfur. Again, all of these diluted 1 to 10 in our solvent, run on our calibration curve, and all of these elements passed within 3% of the certified values for these products. And lastly, we ran the NIST SRM 1085C, which is the Wear Metals in Lubricating Oil SRM. And here you see results that, again, the elements in the darker green are showing us that our results were within 3% of the certified values for those elements. And the ones in the lighter green there were just 3 there, potassium, vanadium, and iron. They were within 5% of the certified values on this NIST SRM. So we were actually very, very happy with these results. And on the NIST SRM, the NIST on the certificate, they give a 95% confidence interval range for the certified value. So in certain cases, we were actually tighter than the results that NIST found acceptable in there. You're welcome to check out the certificate of analysis for the 1085C SRM. I wanted to show this slide just so that you could see that for a metals and oil industrial lab, they're generally interested in low-level elements down to 1 ppm. 1 ppm is about their lower limit as to what is necessary for them to look at. There are certain elements of concern at these low levels. Examples: aluminum, chromium, lead, and tin. We want to be able to say yes or no so that they can see in their trend analysis whether they have to do something or not for their airplane, for their tractor, whatever, So in this slide, it's just an example of showing that our 1 ppm aluminum calibration standard on the 167 line is giving a clear peak that is clearly above the 0 standard. I think you can see it, that the 0 is here, and the 1 ppm is going up there. So that gives us confidence in our low-level results. So just to summarize quickly, in working to help a metals testing lab, an industrial metals testing lab, foremost in their minds is we have to get these hundreds of samples done in a day. How can you help us with that? So what we looked to do was optimize our throughput. A typical sample runtime in a metals testing lab is 1.5 minutes per sample. We were able to get our sample runtime at 2 minutes. I think we could probably make it a little bit shorter, but we optimized the tubing, we optimized the read time. With a very short read time, we have 3-second read time for our samples and our standards, where we're able to give them a usable method. Another request from an industrial lab is, again, make our diluents so that we can make it easy to dilute our oil samples in the diluent, have the cobalt and yttrium in there so that we can just put it in and go. Thank goodness we were able to do that for them. So we have that. This diluent, as I mentioned, I think, can also be used as a rinse. In a real world, in an industrial Wear Metals testing lab, they use their diluent as the rinse. So that is available there. Another thing that is very close to my heart is that we were able to find an organic solvent that's green that's sustainable. So this is moving away from toxic solvents to a place where we all need to go for the people doing the work, for our future generations. And I know that people, these folks with whom we worked, are very happy and interested in this area. So that's about all I have. I just want to mention Inorganic Ventures, and Sergey's going to post all of this. You can look at this and find QR codes to look at our educational resources. Mike Booth developed Ivy Ignite, which is a learning platform for various aspects of testing solutions, Bench Boost podcasts that we do, and traditionally you can go onto our website and look at the technical resources or call us up and ask us, and we'll try to help you out. And we're going to be in Houston December 10th and 11th to do an ICP workshop. So thank you so much, and can I, any questions?
Thank you.
Yeah.
Questions, please.
I got one.
Yeah.
So on the aluminum scan,
Yes.
so I'm clear.
Yeah.
You showed a 1 ppm.
Yeah.
Is that 1 ppm diluted 1 to 10?
No, that's 1 ppm.
So that's a 10 ppm that was diluted down to 1 ppm.
No, sorry, that was a 1 ppm standard.
Right, that you added diluent to. And so in solution, was it 1 ppm?
Yes.
So it was a 10 ppm you started with then. If you diluted it in the diluent, you brought it down.
No, I didn't. I'm sorry. It's, the way we made the standards, I actually didn't get into that. So just saying, for now, that was a 1 ppm standard.
Okay, because in the oils, and I'm sure you know this, the 1 ppm is in the oil. So if you cut it with the diluent, they're actually looking at 100 ppbs in solution, which you would still see. You would plenty of sensitivity.
Thank you, Deal. Any other questions? Okay, yes.
Please. Yeah.
So if I get this right, the primary point here is that you want to get away from organic matrix standards, so that you can use aqueous standards, which are more stable than the organics. Is that correct?
Yeah, yes.
Well, what about the relative cost?
That is something we've considered. And thank you for asking that. The concentrates for the inorganic starting materials, inorganic standards, they're going to be about the same as our inorganic standards that you buy now at Inorganic Ventures. So if you buy a multi-element blend of inorganic elements from us, these inorganic standards, they're going to be about the same. We're working on the final pricing for, and we're not sure when the product's going to launch quite yet, but we'll keep everybody informed. But we're looking at the final pricing for the organic solvent, and my research into that up until now, it looks like it's going to be comparable, really very comparable to your kerosene, to the traditional diluents that are being used. Does that answer your question? Yeah. Okay.
Yeah, the question was about relative cost between the traditional organometallic standards and the approach that Madeline presented.
Yes.
So the composition of the solvent is proprietary.
Yes, the question, the composition of the solvent is proprietary, yes. Anybody else? Well, thank you so much for listening.
Well, once again, we would like to thank you for investing your time, coming up. Hope you learned something in addition to enjoying some breakfast. If you have we want to continue the discussions, we're here. Our booth is number 660. Please come and see us. We will be very happy to answer any of your questions. Thank you.